Ever turn on your tap and just expect a perfectly calculated rush of water to come out? It feels like magic, right? Well, actually, it's all thanks to a massive hidden blueprint of complex engineering right beneath our feet that keeps our cities alive. But how does it actually work? Today, we are opening up the secret engineering playbook in this explainer to make sense of exactly how our modern water lifelines are designed.
So, here's our agenda for today. First, we'll be defining water distribution. Second, we'll look at methods of moving water. Third, we'll dive into dead-end and grid systems. Fourth, we've got ring and radial systems. And finally, number 5, system challenges and leaks. Let's get right into it.
Section 1. Defining water distribution. If you crack open a standard environmental engineering syllabus, the definition goes like this. A water distribution system is the collective facilities used to deliver water from its source to individual consumers. Simple enough, right? But the absolute key here lies in those last 3 words: appropriate quality, quantity, and pressure. You see, it's not just about moving water from point A to point B. It's a massive balancing act. Engineers have to ensure the water arrives with enough pressure to fight a neighborhood fire, all while keeping the entire network economical and easy to maintain.
Moving right along to Section 2, methods of moving water.
Now, before we look at the street-level maps of the pipes, we really need to understand the physical forces driving the water through them. And there is a stark contrast between our 2 primary options here. First, a gravity system. This relies on a high-elevation source, so the water flows down to consumers completely naturally. It is highly economical and deeply reliable because, honestly, gravity never takes a day off. There's zero pumping required. On the flip side, we have the pumping system. Here, treated water is forced directly into the mains using high-lift pumps. But there's a glaring flaw with this one. It relies entirely on a continuous power supply. If the electrical grid goes down, your water supply stops instantly. No way around it.
So, what do we actually do? Well, here is the most common real-world solution: the combined system. Sometimes this is called pumping with storage. Basically, water is pumped from the source into an elevated distribution reservoir. Think of a classic tall water tower. During periods of low demand, like the middle of the night. Then, when the whole town wakes up and jumps in the shower, gravity takes over to supply homes from that elevated tank. It's an incredibly efficient workaround because the pumps can operate at a constant speed, and crucially, you still have water pressure even if the town loses power.
Next up, Section 3, dead-end and grid systems. Let's start looking at the actual blueprints. Picture the oldest, historically unplanned parts of your town. They likely use this setup, which is known as the dead-end system or the tree system. In this layout, you have a single main pipe. From there, submains branch off at right angles, and from those, smaller laterals branch off again. They don't loop back around. They simply lead to several isolated dead ends.
Now, on paper, it's incredibly cheap to install. And calculating pressures is a breeze for engineers because the water only ever flows in one direction. You also need fewer cutoff valves. But that cheap initial cost comes with a massive downside. The biggest issue? Water literally stagnates at those dead ends, which creates a huge pollution risk. Plus, if that single main pipe breaks, everyone downstream is totally out of luck. And because the flow is limited to just one route, it simply cannot meet high fire demand during an emergency.
So, how do we fix that? Well, in stark contrast, well-planned modern cities utilize what's called a gridiron system. You might also hear it called an interlaced or reticulation system. This is specifically designed for cities with perfectly rectangular road layouts, like Chandigarh, for example. In this setup, the mains, submains, and branches are entirely interconnected. There are no dead ends, meaning the water is in constant circulation.
This constant circulation completely solves that nasty stagnation problem. And if a pipe bursts, water can just reroute and come from multiple other directions. It's a real game changer for reliability. But, of course, there's a trade-off. It requires significantly more slice valves to isolate sections during repairs, and you need much longer pipes overall, making it highly costly to construct. Also, because water is sloshing around from various directions at once, the exact calculation of pipe sizes becomes a real headache for engineers.
All right, let's look at some specialized layouts. Section 4, ring and radial systems.
First up in this category is the ring system, also known as the circular system. Notice how the main pipes here are laid out all around the absolute periphery of the rectangular city blocks. They form this giant closed ring around the outside of the area, and only then do the submains branch inward toward the center.
This layout shares a lot of the flow characteristics of a grid. Because of that, it provides excellent water availability from multiple directions, which is fantastic for fire safety. And since it flows consistently from the outside in, engineers actually find sizing the pipes to be surprisingly simple. However, it shares the grid system's main drawback. It demands a really high initial investment. You're going to need extensive pipe lengths and a whole lot of those shut-off slice valves to make it work.
Finally, for localities that have radial road patterns, think of roads spiderwebbing out from a central hub, we have the radial system. The city is divided into different zones, and right in the absolute center of each zone sits an elevated distribution reservoir. The supply pipes are then laid out radially, pushing outward toward the periphery of the zone.
By putting that tank in the center and pushing water outward, this method practically guarantees incredibly high pressure and a very quick, efficient supply to all the surrounding buildings. Plus, the engineering calculations for this setup are surprisingly straightforward. But as you might have guessed, it's a bit of a putting all your eggs in one basket situation. It is highly dependent on those central elevated reservoirs. If something goes wrong at that center hub, the entire zone suffers.
Which brings us to our final topic, Section 5, System Challenges and Leaks.
So, all this pristine engineering theory eventually hits the messy, harsh realities of the physical world. In almost all water distribution systems, a shockingly huge percentage of treated water simply vanishes in transit due to hidden leaks. I mean, just look at the forces working against these underground pipes. You've got internal factors like corrosion, material defects, and this phenomenon called water hammer, which is a sudden, violently damaging spike in pressure. And then you have external environmental factors, the ground itself shifting due to drought or freezing, plus the constant heavy vibrations of cars and trucks driving right above them every single day. The stakes here are incredibly high. As the engineering syllabus plainly states, leaks waste both money and a precious natural resource, and they create a public health risk. When these systems fail, it's not just a puddle in the street. We waste massive amounts of money, we squander our resources, and we create immediate public health risks. This is exactly why maintaining these systems with strict schedules and good public relations is just as vital as drawing up the initial blueprint.
So knowing how much treated water gets lost every single day to these hidden underground forces, I want you to ask yourself, just how fragile is the intricate infrastructure directly beneath your street right now? We hope this explainer has totally changed the way you look at the roads outside your window and leaves you wondering just how sustainable our invisible underground blueprints truly are. Keep questioning, keep learning, and we'll see you in the next one.